Problem 7.2-2. The bent 15 millimeter diameter rod is subjected to the load shown. Determine the state of stress at point A and show the results on a differential element located at this point. Here is the bent rod. Here's our point A. The XYZ axis is shown, and also the dimensions from the forces to point A. We see there's two forces, one force in the X direction and one force in the Y direction, acting at the end of the rod. The first thing I'm going to do is find my internal resultant forces acting at the cross-section where A is located. And there are three possible forces and three possible moments. First I'm going to look at the axial force. That's acting in the Z, along the Z-axis. There'll be an axial force, n sub z, and there are no forces acting in the Z direction, so that's just going to be 0. Now, looking at the shear force in the X direction on that surface, our force in the X direction of 500 newtons will be transferred down to that surface, and it will show up as a shear force. So V sub X is going to be equal to 500 newtons. And that's acting in the positive X direction. There's also going to be a shear force acting in the Y direction from the 250 Newton load. That's going to be a 250 Newton force transferred to the cross-section. That is in the positive Y direction. Now for our moments, there is a moment about our Z-axis, that's the axis of the member, that's going through the cross-section at A, and that is the result of this 500 Newton force, our force in the X direction, acting about this moment arm, which is 30 millimeters. And that's equal to 15 Newton meters, and it's acting about the negative Z direction according to the right-hand rule. There is a moment acting about the X-axis. It is the result of this 250 Newton force here, and it's acting along the moment arm of this 70 millimeters. That equals 17.5 Newton meters, and is acting about the negative X direction. There is a moment acting about the Y direction. It is caused by this 500 Newton force, and the moment arm is 70 millimeters. That gives us a moment of 35 Newton meters, and it's acting about the positive Y-axis. Now to get our section properties that we're going to be needing, we will not be needing the cross-sectional area since we have no axial load, but we will need our moment of inertia, and it's the moment of inertia of a solid circle. So that's pi over 4 times the radius to the 4th power. Our diameter is 15 millimeters. Half of that is 7.5 millimeters, or 0.0075 meters. Our polar moment of inertia is double the moment of inertia, and those values are shown here. Now to find Q. We will need Q when calculating the shear stress for our Vx, internal resultant shear force. Because point A lies on the neutral axis of the cross-section for that shear force, then we need to take the area above or below point A, and that'll be a semicircle. So the A prime for Q of a semicircle is just 1/2 times pi times the radius squared. Y bar prime is the distance from the centroid of that semicircle to its base, and that's equal to 4 times the radius divided by 3 pi. You can find that in reference materials for section properties of various shapes. And that gives us a Q value of 2.8125 times 10 to the negative 7th meters cubed. Now we will evaluate each of our internal resultant forces one at a time to determine the stress, which is a result of the internal force, and then calculating the stress at point A. And we'll begin with our shear force in the X direction. We do have a shear force in the X direction equal to 500 newtons. It's in the positive X direction. The equation we'll use is tau, shear stress, is equal to VQ over IT, where V is our internal resultant force, 500 newtons. Q we calculated above, I we calculated above, T is the thickness of the cross-section at point A, and that's going to be equal to the diameter of the rod, which is 15 millimeters. And plugging that into the equation, we solve for shear stress at point A is equal to 3.77 megapascals, and that is in the positive X direction. Now, considering our shear stress in the Y direction, we do have a shear stress of 250 newtons. and it is acting in the positive y direction, and it passes that stress, as you see, will pass through point A, which is right on the edge, the furthest distance from the neutral axis, which would be the x-axis in this case. And considering the stress distribution for VQ over IT, which would be the shear stress formula, it's a parabola with a maximum at the neutral axis and 0 at the ends. And since A is at the end, A will have a shear stress of 0. That's because Q is equal to 0, because if you take the area below A, which is to the right of A, there is no area. So A prime is 0, so Q is 0. Now the next internal resultant force we want to consider is the torque, which is occurring about the z-axis. And we found it to be 15 Newton meters. And the stress we get from that torque is a shear stress, and we calculate it with this equation, T rho over J. T is 15 Newton meters. Rho is the distance from the centroid of our area to point A, which is the radius, 7.5 millimeters, divided by J, polar moment of inertia, which we found above. And that gives us a value of 22.64 megapascals. And the direction of the stress, well, let's look at the cross-section. The stress is acting in the direction of the torque, which is going around the surface. And at point A, that would mean that shear stress is going in the positive x direction. Opposite of A, on the opposite side of the cross-section, the shear stress would be going in the negative x direction. So at A, I will write that the direction is in the positive x direction. Okay, considering the next internal resultant force, that's going to be our moment about the x-axis. We found to be 17.5 Newton meters, going about in the negative x direction. The stress we get from the moment is a bending stress, and it will be given the equation sigma is equal to my over I, where the moment is 17.5 Newton meters. Y is the distance from the neutral axis to point A. We can see in our cross section the neutral axis in this case would be the x-axis, and the distance from the neutral axis would be the radius from the centroid of the cross section to point A. So that's 7.5 millimeters divided by the moment of inertia. We get the stress, 55.82 megapascals. Now we need to consider what direction this is. If we have a moment going in the negative x direction, that's going to put point A in compression. So I will note that with a letter C, standing for compression. Our last stress to consider is the moment about the y-axis, which we found to be 35 Newton meters. The equation we'll use is the same equation as above, with a little modification. It will be the stress is equal to the internal moment times the distance from the neutral axis, which in this case is the y-axis, so we're going in the x direction, which is perpendicular to the y-axis, divided by I. And in this case, point A, when considering the neutral axis is the y-axis, point A lies on the neutral axis. That means the stress, the bending stress at point A from a moment about the y direction, is going to be 0. And that is because our distance from the neutral axis is 0, since we are on it. So sigma is equal to 0. Now we were asked in the problem statement to show the results on a differential element located at point A. And so here is a differential element. It's a little cube of the material. Represents the tiny bit of material that exists right at point A. And we're going to show our stresses on this cube using arrows. And notice I've drawn the edges of the cube in the direction of my coordinate axes. And let's first consider the normal stress. Well, looking at our stresses that we calculated, we only had normal stress occurring due to the moment about the x-axis, and that was normal stress that was occurring in compression, and that stress is occurring in the z direction. So I'm going to show that on our cube element here with an arrow pointing down and also one from below pointing up, and that stress sigma is equal to 52.82 megapascals. And the arrows show that it is in compression. Now let's consider shear. We have shear stress on this element from two sources. We had shear stress from our our shear force in the x direction, which was 3.77 megapascals in the positive x direction. And we also had shear stress from our torque, which was 22.64 megapascals, also in the positive x direction. So we will show that as a net stress on our element. And that'll be a shear stress of 26.41 megapascals, and it's acting in the positive x direction. And you can see that I showed the shear stress as being parallel to the face of the material, whereas a normal stress is perpendicular to it. For this element to be in static equilibrium, we need to show balancing shear stresses, which means on the underside of this element there will be a shear stress pointing in the opposite direction. On this front face, then, we also have a shear stress pointing up, and on the back face, one pointing down. And this differential element is the solution to the problem. And we are done.